Okay, time for another graphs theory video. So I got some feedback on my last one and it was pretty much that it was hard to follow and the diagrams are unclear, possibly not unrelated. So I'm going to try and fix it up this time by using paint instead of a whiteboard. Hopefully you can follow along. It's still on the same topic. It was once called dividing lines. I've been recommended that I should call it dividing circuits. While the name is still being workshopped, hopefully by the end of this video you'll at least understand what they are and how they're useful, etc. Okay, so to be able to follow along, the prerequisites are you need to know about Kemp chains in 4 colouring, you need to know about proper 3-edge colouring, and you need to know about zonal labelling. If you know about those basics, then let's dive right in. So let's start with a cubic bridgeless map with region size 5 or greater. We're going to zonally label it in 2 distinct ways. So a zonal labeling over here and a different zonal labeling over here. Not just all the values flipped to their opposites, but actually a distinctly different zonal labeling. Next, we're going to compare each vertex labeling to the labeling on its counterpart. And if it's the same, we're going to color it green. And if it's different, we're going to color it red. So something like this. So this here is a 2, it's a 2, so this one we coloured green. Over here we've got a 2 compared to a 1, so we coloured this one red. Hopefully that makes sense. Next, between any 2 vertices which are coloured differently on this map, we're going to add a line. So there's a green and a red, so we'll put a line crossing the edge between the 2 regions. There's a green and a red, we'll put a line crossing between the 2 regions. Once you're done, you should have something that looks roughly like this. I've smoothed the lines out just a little bit to make them more rounded. That doesn't really matter. And at this stage, every time we get multiple lines within a region, we're just going to converge them all onto the one vertex. So we've got multiple lines crossing here. We're just going to have them all connect at the one intersection, with the one vertex. We've got multiple lines crossing here. We're just going to have them connect at the one point. Obviously, if you've got, say, this line came through here and this line came through here, we just connect them up. So we're connecting up all the lines at this stage. Hopefully that makes sense how we got to this map here. Now, what's the point of these lines, you might ask? Well, let's imagine that we don't have our second map knowledge. All that we're given, in fact, we'll take away the colouring again and just leave the dividing lines. So this is all we were given, one zonal labelling of a map and some dividing lines. We could copy that map over here and look at alternating pockets. So for instance, all of this region, all of this pocket, is cut off from the rest of the map. It's enclosed. Sorry, I'll just put a little bit in there. Same goes for this region, or this pocket. I don't have a good word for it. And this pocket, and in fact this one as well. So as you can see, we can always take alternating pockets, alternating sections which are cut off from the other side of the map. And now if we were to change the value of every vertex which is highlighted blue, we would discover that we would end up with our original second zonal labeling. That is, that given a zonal labeling and a set of dividing lines, you can find an alternate zonal labeling. Now, of course, at this stage, we've obtained the dividing lines by starting with 2 different zonal labelings of the same map. So it might not look useful yet, but bear with me. Hopefully, though, what I've covered so far has made sense. I've shown you a way to obtain a set of dividing lines given 2 distinct zonal labelings of the same map. And I've shown how, given one zonal labeling of a map and a set of dividing lines, you can obtain the alternate zonal labeling. Okay, this is a good place to pause and make sure that the part that I've just covered makes sense to you. I'm going to do this a couple of times throughout the video. Every part of the video builds on the previous parts, so if something doesn't make sense to you, then the rest of the video is just going to lose you. So do stop here, make sure that what I've just covered makes sense. Assuming it does, let's dive into the next bit. Okay, so currently we don't have a good way of spotting at a glance whether a set of dividing circuits is actually a set of dividing circuits or just a mess of squiggly lines. So, we can try and apply the whole swapping 1s to 2s in pockets that are alternating and see if that actually produces a zonally labelled map. But there is a much easier way. So this is the same map, except it's properly 3-edge colored instead of zonally labeled. I am going to add a set of dividing circuits, which I've specifically chosen to highlight what I want to show next. Okay, so there are two things that we can do to this map to check that these dividing lines work or don't without having to go through the process of actually changing to a zonally labeled map, flipping vertex labelings to their alternates, etc., etc. We can first color the dividing lines so that they match the edges that they're crossing. So for instance, this line here is crossing a green edge. We're going to color that dividing line green. Down here, crosses a blue with a blue, crosses a red with a red, etc., etc. So that's step one. Step two is to ensure that every intersection looks like this one here. So you have one color going through unaltered, and crossing that color you have both the other colors. So here we have a green being crossed by a red and a blue. That's fine. Here we have a red being crossed by a green and a blue. That's fine. Over here we have a red being crossed by a green and a blue. That's all good. Now if you have a look through all the others, I've specifically chosen this so that this one here does not have that. We have a red turning into a blue and a red turning into a blue. This won't do, but we can fix this. So what we can do, let me just copy the map. We can, instead of just having them connect in the middle randomly like we have been doing, we can instead connect the red to the red and the blue to the blue, like so. Now every line is crossing an edge of the correct color. Every intersection that we have is following the rules that we set forward, whereby you have one color going over and both remaining colors crossing, which means that this here is a proper set of dividing lines. If you were to change everything back to a zonal labeling and then do all the processes to obtain a second zonal labeling, and then you were to change that zonal labeling back into a properly 3-edge colored map, you would definitely get an alternate proper 3-edge coloring of the map. Whereas if you were to do it with this one, you wouldn't. It is a nice, easy way to be able to look at a set of dividing lines and go, yes, that would result in a proper alternative coloring, zonal labeling, or region coloring if you wanted to go through the process of transferring it to that as well. So yeah, the two checks to make sure that there are a set of dividing lines. First, make sure there are only vertices of degree 4, or 2 or 4, I guess, depending on how you look at it. And second, make sure that every degree 4 vertex is following the coloring rules. If you can do that while still making sure that every edge is crossing an edge of the appropriate color, red to red, green to green, blue to blue, then you have a set of dividing lines without having to check through other means. Okay, another good place to pause the video and go back through and make sure that what I've just covered makes sense. If you've made it this far and it does all make sense, then congratulations, you now understand what dividing circuits are. The rest of the video is going to be broken up into parts of different uses for them, ways to find them, tying them into the 4-color problem, a couple of things like that. But what's covered so far is, I would say, the basics of them. So do make sure that it all makes sense, otherwise again the rest of the video will almost certainly be a bit confusing. Assuming it does make sense though, let's dive into the next bit. Okay, so we're going to keep on looking through the properly 3-edge colored lens. At the moment, in order to play with dividing lines and actually obtain an alternate coloring of the map, we would need to go through zonal labeling. That's a bit of a hassle, so we're going to find a way to bypass that completely. So here is the previous map that we were using, exactly the same. I am going to add a nice simple set of dividing lines over the top. Very easy to check with this one. There's only a few intersections. They're all following our coloring rule, and all the edges are crossing edges of the appropriate color. So this is a proper set of dividing lines. But we now go, well, we don't want to go into zonal labeling and back again. So instead, we're going to introduce this little chart. It might look confusing at the moment, but it'll become simple in just a couple of seconds. And in fact, after doing this a few times, the chart actually becomes unnecessary. It becomes quite simple to just do it without the chart. But for the first time, we'll use the chart. So here is the map. We're going to properly 3-edge color over the top. So what we do is we choose any pocket of this map and correlate it to any one of the 6 corners of the chart. So we're just going to choose the outside region for a first one. We have to do every region, every pocket. We're going to choose the outside and correlate it to no change, just for convenience. You could choose any of them and it would work. Feel free to play around later if you want, but we're going to choose no change for the outside. So we can color that bit in right away. Okay, there we go. No change to that pocket. As you can see, where the dividing lines are, we stopped coloring, leaving us with a whole lot of half-colored edges, you might say. That's okay, it's only temporary. Let's look at the next spot. So let's choose in here. We could choose any spot, but I'm just going to choose in here arbitrarily. To get from here, this pocket to this pocket, we cross a green line. So this was our first pocket, we cross a green line, we get to here, we change red to blue and blue to red. Green doesn't change. So we can do that right now. So anything that was green stays green, anything that was red turns to blue, and anything that was blue turns to red. So we finished the green lines, the green edges, I'm sorry. The red line is no longer red, it is blue. The blue line is now red. And we can go on to the next zone, or the next pocket. So let's have a look in here. To get to here, we started from this pocket, which was the outside. We crossed a green line, so we got up to here. And now we're crossing a blue line. So from here, crossing a blue line, we get to here. Now green edges become blue, blue edges become red edges become green. Let's do that. And done. And now on to the next zone. So let's have a look at this one. Now here, we could either start from this area, the no change on the outside, and cross a blue line, in which case we end up here, or we could start from the no change, cross a green line, a blue line, and then a red line. But you'll notice green, then blue, then red, we still end up here. It doesn't matter what pathway you take, you're always going to end up at the same part of the chart that we've got happening here. And that's thanks to the intersections following the coloring rules that we laid out before. You can play around with that in your own time. It's a little bit of fun, but for the time being, I'm just going to color in this next section. There we go. Only 3 sections left to color in. We've got this pocket. Again, I don't have the right terminology locked in for this stuff yet, but this one, and this one. So let's do this one next. There we go, fairly straightforward. We were just swapping all the greens to blues and all the blues to greens in that pocket. Next pocket, might as well do this one here. If you're getting lost, you can always, this is why I choose to go no change on the outside, so I can always follow it back in. Again, that would work with any combination, but going from no change, we're crossing a red and a blue, so we cross a red and a blue. So here we are here for this one, green to red, blue to green, and red to blue. So for instance, this blue edge here, which would be half done, we are turning green, which is correct. It's a nice easy check to make sure you haven't made a mistake along the way. So color that one in green. Green turns to red, which is correct. That's what's happening, as we can see from our half finished edge. The red turns to blue. And rinse repeat for the other edges. Fairly straightforward. And now the last one we've got to do is this pocket here. Easiest way to figure it out is to go from no change over to green, over the green, so red to blue, blue to red, and no change for green edges. So red to blue, red to blue, no change for green, no change for green, and lastly blue changes to red, and the end result after all that is we have an alternate proper 3-edge colouring of our original map, and we haven't had to go through changing the 3-edge colouring to a zonal labelling and then transferring over the dividing lines and etc, etc. We just bypassed all the steps and just came up with an entirely new acceptable labelling for the map. Again, this chart, it's useful for getting your head around why this works initially, but once you've played around with it for a little bit, it becomes second nature to just go, oh, okay, outside no change, we cross a green line, and because you're crossing a green line, you know that blue and red change, and then you can do that for I crossed a blue line, I crossed a green line, I crossed a red line, and then it all sort of falls into place. It's again, feel free to use the chart as long as you need to, but yes, after not very long of playing with these, it does become second nature, where you start with a map with some dividing lines and you go, hey, I can check if those dividing lines are correct or not, whether they will lead to an alternate colouring, and you can also just jump straight to the alternate colouring if that's what you want to do, making this a rather convenient addition to our graph theory toolset that we have on hand. Okay, another good place for a pause. I realise there's a lot of information being thrown at you this video fairly quickly. I don't expect anyone to be able to just sit down and watch the video beginning to end and go, oh, now I understand everything about dividing circuits. It is going to take a lot of pausing and rewinding and rewatching and figuring stuff out. I've been at this for a long time and I'm still figuring out stuff about them. That being said, just like before, if there's something you don't understand in that last section, it'd be wise to stop and go back and make sure you understand it, because the next section will build on it again. Yeah, if you do understand it though, then let's dive into one more section. Okay, so as you've probably figured out by now, one colouring of a map can have many different dividing circuits which can overlay it. Here are two that we've already covered in previous sections. This dividing circuit led to this colouring scheme. This dividing circuit, we never actually looked at what it led to in this colouring scheme. We know it does because the intersections are all right and the edges are all right, but we never actually followed it through. The question becomes, is there a way to easily determine the dividing lines which would be necessary to go from this map here to whatever this map turned out to be, without having to first check out this and go properly 3-edge colour it, and then take both of these maps back to zonal labelling, and then compare their vertices, and etc, etc. Is there a nice simple shortcut? And the answer is yes, there is. It's a little bit messy, so bear with me, I'll do my best to make it clear. So the first step is we're going to look at every dividing line which is overlaying this map, and anywhere where there's a dividing line on this map which is the same, we are going to colour it in brown. So for instance, this one here, that correlates to this one here. Just over here, that correlates to there, and in fact there. And we keep on going through. I've chosen two maps which are deliberately similar, but they've got enough differences so that we can see what's happening. Relatively easy come the end. So it's a little bit messy here, so forgive me for not colouring in between the lines perfectly. We'll continue on from up here where we started. Okay, in addition to colouring in the lines which are on both brown, if there's a line here which doesn't exist on this one, we're going to introduce a new colour. I'm going to choose light purple just because it stands out a little against the other colours which I've used so far. I've obviously missed a brown line, I'm sorry. There's one going through here, up here, that turns purple, because it doesn't exist on this one. Purple, and that little line there is brown. Okay, hopefully that makes sense as to what I've done so far. Maybe not why I'm doing it, but hopefully you can see what I've done. The next step is we're going to go playing on this map up here. The first thing to do is any line which existed on this secondary map's dividing circuit but is not coloured brown, we are going to move onto this map and colour it the appropriate colour. So starting off with a nice easy one, this line wasn't covered over, so we can just add that in and it stays green, there's no change there. Going down, this is green. Now here, you'll notice that this line, even though it was red in this one, it's going to be green. So we keep it green. We have a look, even though it was red in this one, it's going to be blue. Blue again. Back to green, and we do this for every line that wasn't coloured in. So this is the end result, and the last step is to look at these purple lines which we added going through here, and we're going to put them onto this map as well, colouring them in appropriately by what edges they cross. So that purple line crossed a red edge here, crosses a red edge there. There's a purple line going up here which would be red. Continues on through there. I believe that's all of them. At this stage we would double check our intersections, much the way we did with this dividing line back in the day. We would check that all the intersections are one colour going through and both the other colours crossing, which they are in this case. And now, without having gone through any steps or even looking at what this map is, we can say with certainty that if we were to use these dividing circuits on this map colouring that was drawn over, we would end up with whatever colouring this map was going to be had we followed these circuits. It is just a shortcut which allows you to jump between various map colourings without the need to play around with a whole lot of middle steps. I appreciate that this process looks a little bit confusing, colouring it brown, adding in purple, etc, etc, but it is actually quite simple. And much like most of the other steps so far, it's just a matter of practicing until you get the hang of it, and then it becomes like second nature. Okay, quick pause time again. Good news, that last section is probably the most complicated section of this video, so if you've got through that, then it's all downhill from here. Once again, check over it, make sure you followed it. The next section goes off in a little bit of a tangent compared to previous sections. It is still related to dividing circuits, but it's time to relate them back to the four colour problem. Okay, if we're ready, let's jump on in again. Okay, just going to squeeze this in at the start of this section because it's quick and easy. When looking at dividing lines overlaying a four coloured map, it is perfectly possible to quickly check whether the lines are correct or not in a similar way to the way that we did with properly three-edge coloured maps. So here's a set of dividing lines overlaying a four-coloured map. If we have a look at, say, this line here, it's going yellow, red, yellow. At the intersection, it's going green, red, and blue, red. This happens at every intersection. You have one Kemp chain, which goes directly straight through. So here it is again, yellow, red, yellow. And then either side of that intersection, you have the two other possibilities. So green, red, and blue, red in this case. It's not as easy to untangle lines. So if you've got a region which is, say, size 12 and you've got a dozen lines going in and you're trying to figure out whether the lines can cross in a way which allows dividing lines to work, it can be trickier to figure out. But just generally, it's worth noting that this is the way that the dividing lines work when overlaying four-coloured maps. So blue, red, blue at this intersection, following that Kemp chain. So the other Kemp chain is yellow, red, and green, red. Whether or not this fact is particularly useful, I guess that might be debatable, but this felt like the point to stick it in. Okay. So it's time to look at what happened in different labellings when using dividing circuits. So let's say this is an edge in a map, doesn't matter, and we have a dividing circuit going across, or a dividing line going across in this case. When we go through and change the labeling to an alternate version, this edge will always end up as one number will stay the same, one vertex labeling will stay the same, and one vertex labeling will change. Pretty straightforward, and while we didn't explicitly mention it at the start of the video, it was pretty well covered by what happens to an overall map when we start playing with things. Okay, so moving on to properly 3-edge colored maps. If we start with an edge like this, and we'll add our dividing line over again, and we do our changing the coloring to an alternate coloring, we could end up with something like this, where on one side it all stays the same, and on the across the line we've swapped a couple of the edges around. There are other possibilities, obviously, for 3-edge coloring. Possibly both sides change a little bit. That's okay. We are more worried about what happens in a 4 coloring layout. So let's assume that this is the setup that we have, green, green, blue and red, and we have a dividing line going through. Now, whatever happens to the specific colors, once we change things around, we are always going to end up with a situation where 2 regions separated in this manner, which were the same color, will end up differently colored after the dividing circuits have been used. So this is just one possibility where, again, this side of the dividing line didn't change, and on this side of the dividing line we changed just the one color, green to yellow. This is the important one, at least for what I'm about to cover. So let me just put this aside. So let us assume that we have a hypothetical minimum counterexample to 4 coloring. So here's an edge within that hypothetical minimum counterexample, and this region here is the region that we can't color. We can color every region except for this one. Okay, so following that logic, if we were to remove this edge here, like so, let me just tidy that up a little bit, then we would have no problem in coloring the map now that there is one less region in it, and let's call this region that we've colored green. Hopefully that all makes sense. Okay, so if we can do that, then we can also reintroduce the line that we removed and add one extra one, and the result is a 4-colored map with this little 4-sided region in here. Now, the 2 regions either side could be both the same or both different. Let's start with them both the same, and I'm going to convince you that I can make them both different every time. So we are going to try and use Kemp chains to change one blue into a red. Now, if we can't do that, that means that there is a blue-red Kemp chain going all the way around there. If that's the case, then we can use that in order to color the map like so, which might not seem particularly useful, but remember, this was our starting map. If we now apply those colors to here, then we have a properly 4-colored minimum counterexample. That can't be the case, so therefore we must always be able to change, in this situation, one blue to red. So let's just do that now. Great. Now we're going to modify the map one more time by removing the 4-sided region entirely and connecting the red to the blue, like so. And at this point, I need you to remember what happens when we have 2 same colored regions either side in the setup of a dividing line. So if we were to be able to, not that we can prove that we can necessarily, but if we were to have a dividing line down here, when we obtain our alternate coloring from activating the dividing circuit, we're going to be left with a coloring something like this, which of course we can apply to our original setup, and hey presto, we have a properly 4-colored minimum counterexample to 4 coloring. So that was all a bit of a long way of showing that if you can prove that you can have a dividing circuit going through any edge of your choice on a map, then you can use that to prove the four-color theorem. Now, I should point out that by changing the map around like this, we have to extend the maps that we're working with from purely maps of region size 5 or greater to maps of all regions of size 5 or greater, but you can have one region of size 4. Starting on region size 5 or greater maps is a great way to introduce dividing circuits, and it may be possible to do a similar proof to what I've just done here, but only using guaranteed 5 or larger sided regions. But that's okay, as dividing lines seem to always work, except for when you're talking about 3-sided regions, or more interestingly, when you're talking about an odd-sided region surrounded purely by 4-sided regions. So if we were to have a map like this, for instance, it is not possible to get a dividing circuit which goes through whatever the labeling system that you have. It is not possible to get a dividing circuit which will, say, pass through this edge. This is starting to look at pretty niche corner cases. I prefer to play with maps which are region size 5 or greater generally. I only ever include one 4-sided region when I'm trying to prove the four-color theorem. You might find other situations when using multiple 4-sided regions which cause troubles for dividing circuits. But whatever the case, this was just a nice, simple, or at least the simplest that I know of, proof for showing that if you can show that you can get a dividing circuit overlaying any map such that one of the lines goes through an edge of your choice, you can use that to prove the four-color theorem. Without the aid of a computer, that is. Do feel free to polish this up if that's your sort of thing. I do appreciate that this is not a particularly elegant approach. Okay, cooking with gas now. That's pretty much the end of things at this point, actually. Once you go back and make sure you followed it, and etc, etc. You might be looking at, well, hang on, the video's still got however long left to go. There are 2 more segments that I want to include, but these 2 segments are not polished, so everything so far has been figured out and worked out and thought about fairly carefully, etc, etc. The next 2 segments are, I would say, works in progress. They're ideas that I'm tinkering with. I think they're interesting. I hope that you find them interesting. If you've followed along this far and know what we're talking about now, I definitely think you'll find them interesting. But yes, they're not polished, they're not refined, they're still pretty raw. They're very open to being workshopped. Not that everything else wasn't, of course. If you've got feedback or ideas on anything covered so far, I would love to hear from you. And yeah, thanks for sitting through all that and hopefully trying to follow it. Okay, with that, let's jump into the second last segment. Okay, so far most of the focus has been on dividing circuits overlaying properly 3-edge coloured maps. That's because that's where we can get the most information and it's easiest to untangle the lines and make sure that they're correct and not just a bunch of squiggly lines. But there are some advantages to working in 4 colouring systems. So after a while, you learn a couple of shortcuts. So I can see this map and go, okay, there's a couple of greens there. I could have a line going like so, a line going like so, and then zip around here, for instance. And that's a perfectly acceptable dividing line. If you were to translate it to a properly 3-edged coloured version of the map, all the intersections would be following the rules that we've established. And that's just being able to spot these things in the layout. And after a while, here's the map from earlier, you can start seeing them crop up everywhere. So here's one here, and here's one here, and here's the other map that we looked at, and you can see another around there, there's one. They start popping up everywhere, and the more that you look at these maps, the more features you can spot which make it easier and easier to come up with dividing lines on your own. I personally find that 4-colored maps are the easiest way to do this. I did at one stage sit down and try and put together a list of all the little patterns that you see emerging out of these things, but I realized it was never going to be a complete list. However, I'd like to share with you one little way of thinking about things which I think helps clarify what's actually happening. Okay, so here we have a hexagonal grid coloured in repeating patterns, and we're going to use this to represent every 4-coloured map you can have. Now obviously it's not a region to region map, it's more focusing on Kemp chains. So we have green, blue and orange, red going from left to right. We have blue, red and green, orange going up left to down right. And we have blue, orange and green, red going from top right to bottom left. This breaks down the Kemp chains into 3 groups. So if you can imagine that these chains either go and loop around on the side here, or they dead end as there are other chains looping around and going up and up and up. If you can imagine that if you this row here might be the same as this row here, like it'll eventually repeat, so it just cycles around. With this very broad perspective of maps, we can have a look at what happens when we're doing a dividing line following a Kemp chain, so in this case following a green-blue, and when it breaks off into different directions at an intersection, it might say go like this, and this is following the equivalent of the colouring rule that we had earlier, where we have one going straight across, the Kemp chain going straight across, and then the 2 ones coming in from either side. And then we can keep on doing this, so we can, I don't know, we could do something like that, and let's say this Kemp chain actually loops around here and loops around here, just to keep it simple, and then when we get down here, we go in this direction. And as I was saying, those ones correlate to somewhere up here, so you're actually coming down like so. And then, okay, I didn't line these up, so it's going to get more complicated, but that's okay. The point being that what you're trying to do is connect the Kemp chains by following these rules. Now obviously if it was this simple on maps, then it would be easy to show that yes, you can always have a dividing circuit overlaying any map and going between any 2 regions of your choice. Clearly there are a bunch of corner cases that aren't covered by this very broad simplification, but I just thought it might help people understand why it's actually so easy to connect up the dividing lines overall. They're going in 3 directions. They're going left, right, diagonally, or the other diagonally. When they intersect, they kink, and all we're doing is following them through to their natural progression until eventually they line up with each other. I probably should say that if this doesn't help clarify things, really don't stress on this bit. It was just an interesting perspective, I thought, on dividing circuits. But if you're finding that this is confusing you and you'd rather just focus on proper 3-edge colorings and dividing circuits overlaying those maps, then by all means. I realized pretty quickly that this sort of viewpoint wasn't going to lead to a proof, but again, for the purposes of wrapping your head around things, I don't think it can hurt. Okay, right near the end now, 1 segment left to go. So I have saved the most confusing part for the end, not just because it's at the end of the video and I don't know who's still left watching, but it's also what I'm currently tinkering on, what I'm working on. Not only have I not figured out necessarily how to communicate it properly yet, because I'm still sorting it out in my head, but I also haven't gone through and dotted all the I's and crossed all the T's, so to speak. It is very much current work. That being said, I feel it deserves inclusion in the video because it is very much on topic, and where else am I going to talk about this sort of thing, really? Yeah, like all the other segments, if you've got any feedback, then I'm all ears. But for this segment in particular, if you find that you can't follow it, really don't worry about it. Like, it's honestly as much for me as it is for you, just to get my thoughts in order. Okay, that little disclaimer being said now, let's jump right in. Okay, so let's return to our properly 3-edge coloured map. We're just going to use the same one as before. Now what happens if we add in a new edge and then properly 3-edge colour this map? Well, you might get something that looks like this. Now let's add dividing circuits where we can. We could go back through zonal labeling and compare vertices and then get them that way. But as you probably suspect, it's perfectly possible to draw them without doing that and just staying in a 3-edge colored format. The result will look something like this. Now, most of this will look okay, but you might be noticing in the region where we introduced an edge, something funny is happening. We have, I'm sorry, I can probably connect red to red and red to red so that we're at least obeying intersection coloring rules. But as you can see, we have a red line crossing a blue edge and again a red line crossing a green edge. I guess you could call this type of dividing circuit type B, while the other one would be type A. Again, this is relatively new stuff, so I don't have a name for it at all yet. Now this works for any edge introduced where the new resulting map can have a proper coloring, and it has a couple of potential uses. So just going to focus on some very specific scenarios. So here is just an edge. If we were to translate it into zonal labeling, the labels would both be the same, so 1 and 1 or 2 and 2. Now let's imagine that this is part of a larger map, and when we introduce an edge resulting in a size 4 region, we get a coloring something like this. Okay, like before, let's focus on the dividing circuits that would be needed for this. This is what the dividing circuits look like, leading into this. Whatever is happening outside of here, this is the part that we're focused on. The blue line crossing a green and the green line crossing a blue. The reason that this is interesting is we can now take this dividing circuit type B and convert it back to a dividing circuit type A. So what we can do is we can have a look at our original map, where this was the only part that we knew about, and we know that it's possible to have a dividing circuit that's blue, sorry, let me make that a bit clearer, a dividing circuit that's blue coming in from over here, a dividing circuit that's red coming in from over here, red coming in from over here, and green coming in from over here. So what we can do is we can make a regular dividing circuit, type A for lack of a better term, and connect them up like so. And we have just shown that there is a dividing circuit which can overlay the map, which intersects this edge, which has vertices both labeled the same. Now you can play around with how to introduce four-sided regions of particular types into maps, etc., etc. But it is interesting. Before I was saying that the four-color theorem could be proved without the use of a computer if you could show that you could have a dividing circuit overlaying any map such that a desired edge is crossed by one of the dividing lines. While that's true, technically we only need to be able to cross edges which are both labeled differently. That's a little side thing which I'm not going to go into great detail here. I possibly should have covered it a couple of sections ago. I'm sorry about that. But here it looks like we've got a potential method to at least show that dividing circuits can exist on any map, and more than that, a way to show that they can always cross an edge where the vertices are labeled the same. Is that a stepping stone towards showing that they can always cross an edge whose vertices are labeled differently? Or is this a bit of a dead end? I don't know. I've been playing around with them a lot, and there is a lot you can do with them. But as they're still quite new, and also I appreciate quite confusing, at least on first glance, I'm just going to leave them there as is for now without going into much more detail. So if you want to play around with them yourself, I do encourage you to do so. I haven't got to the point where they come naturally to me yet. I still have to look at the maps and go, oh, hang on, if this goes there, then that's got to be that color, and like it's not second nature for me yet. Whether it will be in time or not, I don't know. But yeah, maybe next video I'll have more information on them for you. And that is everything. thanks very much for watching. Not really much left to say. If you've got any feedback, please do let me know. Otherwise, catch you next video. See ya.